Beneath the ocean's surface hides a predator armed with 18 venomous spines, capable of inflicting pain so intense that some victims call it unbearable. While its beauty lures collectors and stuns rivals, scientists now rank its venom system as the deadliest among all reef fish. But why has evolution handed the lionfish this perfect, ruthless arsenal? The answer explains not just the lionfish's dominance, but also why no diver or prey in its path is ever truly safe. Inside every lionfish spine, a hidden arsenal waits, an intricate cocktail of proteins and enzymes designed to attack at the molecular level. When a spine punctures flesh, the venom flows from specialized glands at the base, traveling along grooves on the spine into the wound. This is not a single toxin, but a complex blend of neurotoxic peptides, hyaluronidases, phospholipases, and proteases, all working in concert. The neurotoxins target the nervous system by binding to sodium channels on nerve cells. That binding blocks the electrical signals that control muscle movement, causing paralysis and a surge of excruciating pain. Even a small dose can overwhelm the body's defenses. Pain can begin in under a minute and last for hours or even days. Hyaluronidase enzymes break down the connective tissue around the injury, allowing the venom to spread rapidly through muscle and skin. Phospholipases disrupt cell membranes, damaging tissues and sometimes triggering cardiovascular symptoms. Proteases chew through proteins in the blood, amplifying swelling and tissue damage. The result is a coordinated biochemical assault that leaves nerves firing uncontrollably and muscles locked in spasm. Not every lionfish carries the same punch. The potency of the venom varies by species and even by individual, but what unites them is the efficiency of their neurotoxin delivery. In laboratory tests, venom from Pteroa miles wiped out more than 3/4 of liver cancer cells at low doses, evidence of its raw biological power. In the wild, this molecular weapon ensures that predators and prey alike learn to keep their distance. As Dr. Morales explains, the lionfish's venom does not just defend, it dominates, turning each spine into a microscopic lockpick that jams the body's most vital systems. The next question is how this biochemical threat reaches its target so reliably every single time. Measured by any single yardstick, the ocean's venomous fish present a brutal contest. But when potency, delivery, encounter rate, and anatomical arsenal are stacked side by side, the lionfish emerges as a unique threat. A composite index brings the competition into sharp focus. On one axis, the lionfish's 18 venomous spines set it apart, 13 along the dorsal ridge, 3 on the anal fin, and 2 pelvic, each loaded with neurotoxin and ready to puncture. Stonefish, often cited as the deadliest by laboratory standards, wield just 13 dorsal spines, and their venom has a lower LD50, meaning a smaller dose is needed to kill half of test subjects. By raw toxicity, stonefish venom can be up to 100 times more potent than lionfish. LD50 values for stonefish have been reported as low as 0.025 milligrams per kilogram in mice, compared to lionfish's 2 to 10 milligrams per kilogram. But the story does not end there. Venom yield per sting adds another dimension. The stonefish can deliver up to 100 milligrams of venom in a single strike, while lionfish typically release less, between 0.1 and 2 milligrams per spine. Yet the lionfish's advantage lies in numbers. Multiple spines can puncture at once, multiplying the dose, especially in close encounters. Human sting data reveal a different kind of danger. In the Indo-Pacific, and now in the Atlantic, lionfish are responsible for hundreds of documented injuries each year, a number that continues to climb as their range expands. Stonefish, despite their notorious reputation, cause fewer stings globally, partly because their habitat is more limited, and their exceptional camouflage keeps them hidden from swimmers and divers. When venom potency, venom yield, frequency of human encounters, and spine count are combined into a single danger index, the lionfish consistently ranks near the top. It may not possess the single most lethal venom, but its array of 18 spines, the efficiency of its delivery system, and its increasing contact with people put it in a class of its own. This composite threat justifies its reputation as the ocean's most venomous fish, not by chemistry alone, but by the sum of its biological weapons and the frequency with which they are deployed. 18 venomous spines form the lionfish's most formidable weapon, 13 along its back, 3 beneath the tail, and 2 jutting from the belly. Each spine is a marvel of natural engineering, shaped not as a simple needle, but as a solid tri-lobed rod with deep grooves running its length. At the base, clusters of secretory cells churn out potent venom, packing it into the grooves under a thin, flexible sheath. When a spine pierces flesh, the sheath peels away and the grooves open, channeling venom from the base to the tip in a single, smooth flow. There is no muscle-powered injection, just the mechanics of puncture and pressure, perfectly tuned by evolution. The design is precise. The tri-lobed cross-section adds strength, allowing spines to penetrate tough scales or even gloves, while the paired grooves act as miniature canals, delivering a measured dose of venom directly into the wound. With each movement, the lionfish can raise or lower its fins using specialized muscles at the base, locking them into place for defense or folding them flat for stealth. The dorsal spines, longest and most visible, fan out in a display that warns off predators and rivals alike. Anal and pelvic spines are shorter, stiffer, and angled for close-range protection, capable of absorbing sudden force without snapping. What makes the system so effective is its passive delivery. The moment a spine punctures, venom is released automatically, with no need for the fish to bite or struggle. Multiple spines can strike at once, multiplying the dose and overwhelming even large threats. Fragments of broken spine can remain embedded, continuing to release venom and prolonging pain and tissue damage. In the wild, this arsenal ensures that few creatures risk an attack. When the lionfish hunts, those same spines serve a dual purpose, forming an impenetrable barrier as the fish herds its prey, and standing ready to punish anything that gets too close. A shadow flickers above the coral as the lionfish glides into position, fins extended like a living fan. The hunt begins not with a sprint, but with a slow, deliberate dance. Each movement is calculated. The lionfish spreads its pectoral fins wide, forming a wall of spines and rays that blocks every possible escape route. Small fish and shrimp sense danger and dart for cover, but every gap is sealed. Prey are herded into a shrinking corner, their exits closed off by the lionfish's living barricade. Dr. Ravi Singh, a marine ecologist, describes the choreography. It is like watching a chess master. The lionfish moves with such precision that the prey has nowhere to go. Every angle is covered. In controlled studies, researchers observed that lionfish succeed in nearly every attempt. Their hunting success rate approaches 100%, a figure almost unheard of among reef predators. On some reefs, a single lionfish can consume up to 30 prey in a day, swallowing fish half its own length in a single gulp. The feeding is relentless, the efficiency astonishing. The lionfish's mouth opens with a sudden vacuum, sucking in its target whole. There are no second chances for the prey. Once trapped within the ring of fins and spines, escape is impossible. The venom-tipped spines, so effective in defense, also serve as a tool of dominance. Prey must choose between a mouth lined with teeth and a wall of venom. Most do not survive the encounter. Time and again, this ambush strategy plays out across reefs from the Red Sea to the Caribbean. The lionfish's design, with fan-like fins, rapid reflexes, and a mouth built for suction, turns every hunt into a near-certain victory. In the world of coral predators, few can match this level of predatory precision. Bands of crimson, snow white, and deep chocolate ripple along the lionfish's body, each stripe more vivid than the last. These colors are not just for show. They serve as a living billboard, warning would-be predators that danger lies within. In nature, this kind of visual signal is known as aposematism. Across the Indo-Pacific, few animals risk a bite when faced with the lionfish's electric palate. Even large groupers and moray eels, notorious for their appetite, tend to keep their distance. The message is clear: approach at your own peril. But what deters predators in the wild has a very different effect on people. The same striking beauty that warns off natural enemies has made the lionfish a prized addition to home aquariums. Since the 1980s, demand for exotic marine fish has fueled a global trade worth hundreds of millions of dollars each year. Lionfish, with their flowing fins and hypnotic movement, quickly became one of the most sought-after species among hobbyists. In the United States alone, thousands are imported annually from Indonesia, the Philippines, and beyond, often traveling thousands of miles in plastic bags filled with seawater. Trade data from the early 2000s shows lionfish among the top 10 most imported marine ornamentals, outpacing many native reef fish. This appetite for beauty comes with hidden costs. Hobbyist demand has created a steady pipeline from reef to living room, but it has also paved the way for ecological disaster. When aquarium owners, overwhelmed by the care required or unaware of the risks, release unwanted lionfish into local waters, the consequences ripple outward. In the Atlantic and Caribbean, these releases have seeded a population boom, with lionfish now numbering in the millions. What began as a fascination with beauty has become a global invasion, driven by the allure of those warning stripes. The lionfish's colors, once a shield, now serve as a passport, opening new frontiers both in trade and in the wild. In the Indo-Pacific, the lionfish perfected its design over millions of years, shaped by a world where survival demanded both offense and defense. Coral reefs there teem with predators, moray eels, groupers, and sharks, forcing every resident to adapt or disappear. For the ancestors of today's lionfish, this meant an evolutionary arms race. Only those with the most effective protections and hunting tools survived to pass on their genes. Venom became their answer. Across countless generations, mutations that increased venom potency or improved spine structure gave lionfish an edge. With few fish willing to risk a mouthful of spines, the brightest colors became a warning, not a target. The lionfish's bands of red and white, so striking to the human eye, evolved as a clear message to would-be predators: approach at your own risk. In this environment, natural selection favored individuals with stronger, more complex venom and more prominent spines. Over time, the arsenal grew. 13 dorsal spines, 3 anal spines, and 2 pelvic spines, each equipped with its own venom gland. But the evolutionary story goes beyond defense. The same traits that deterred predators also made the lionfish a master hunter. Their fan-like fins, originally evolved to make the fish look larger and more intimidating, proved just as useful for corralling prey. This dual purpose, protection from predators and hunting efficiency, set the stage for the lionfish's rise. Genetic studies show that lionfish populations diverged and spread across the Indo-Pacific, adapting to different reefs, but always retaining the core features: venomous spines, vivid warning colors, and ambush strategies. With few natural enemies left, and an arsenal honed by the pressures of their native seas, lionfish populations remained balanced in the Indo-Pacific. Their evolutionary toolkit, venom, color, and hunting prowess, was perfectly matched to the challenges of their home waters. But when these same traits arrived in new predator-free environments, the outcome would be very different. In the turquoise shallows of the Bahamas, the numbers tell a story of collapse. Surveys now count up to 390 lionfish per hectare, densities unheard of in their native Indo-Pacific. Where these invaders appear, native fish populations plummet. Parrotfish, wrasses, and damselfish vanish at rates of 60 to 90%, leaving reefs stripped of their grazers and cleaners. The cascade does not stop at fish. Algae smothers the coral, unchecked by the missing herbivores, and the reef's architecture begins to crumble. Fisheries that once brought in $50 million a year now struggle, with revenue falling by nearly half as the ecosystem falters. Local dive operators organize derbies and haul out thousands of lionfish in a single weekend, but the tide keeps rising. Marisol Perez, a marine biologist who has tracked the invasion since the early 2000s, says that when she started, the reefs were noisy and full of life, and now, in some spots, it is just lionfish and silence. With no natural predators in the Atlantic, the lionfish's arsenal of venom, spines, and hunting prowess has become an unchecked force, transforming vibrant reefs into ghost towns. Alex Johnson never saw the lionfish until it was too late. While culling invasive adults off the coast of the Bahamas, his gloved hand brushed against a cluster of spines. 5 punctures, deep and immediate. Within seconds, his hand felt as if it had been plunged into boiling oil. Paralysis crept up his arm. By the time he reached the surface, the pain had become unbearable. Waves of burning, muscle spasms, and cold sweat washed over him. Emergency crews rushed him to the hospital, but there was no anti-venom to offer. The only defense was time and heat. Doctors immersed Alex's hand in water heated above 45 degrees Celsius, hot enough to denature the venom proteins. The pain eased after 90 minutes, but the swelling lingered for days. Long-term nerve damage left him with a permanent loss of feeling in 2 fingers. Hundreds of people are stung each year, most in the Indo-Pacific, but numbers are rising in the Atlantic as lionfish spread. Divers, fishers, and swimmers are all at risk. The recommended first aid is immediate hot water immersion. Vinegar, often used for jellyfish, does not help with lionfish venom. Severe cases can cause lasting weakness, allergic reactions, or even temporary paralysis. With no antivenom available, prevention and rapid response are the only safeguards. For Alex and many others, the lesson is clear. Respect the warning stripes and never underestimate what hides behind their beauty. In a quiet lab perched above the Carolina coastline, Dr. Maya Cheng and her team are transforming a threat into hope. Using advanced fractionation, they isolate peptides from lionfish venom, tiny protein chains that in the wild paralyze and inflict agony. Here, those same molecules are being reimagined as the next generation of medicine. Early trials reveal a remarkable property. Certain venom peptides block pain signals in nerve cells without the addictive risks of opioids. For patients with chronic pain, this could mean relief without dependence. In parallel, other fractions show activity against cancer cells, halting their growth in petri dishes and triggering cell death in ways traditional drugs cannot. The research has reached Phase 1 clinical trials, a cautious but real step toward human treatment. Dr. Cheng describes the paradox. What once terrified divers may one day heal them. The ocean's most venomous fish, once a symbol of danger, is becoming a source of hope. Proof that even the sharpest weapons in nature can be turned toward healing. Right now, lionfish venom is both a threat to ocean ecosystems and a potential source of medical breakthroughs. As populations surge unchecked in the Atlantic, their impact on native species intensifies each year. The line between danger and discovery remains razor thin, reminding us that today's deadliest adaptation could become tomorrow's life-saving solution. Nature's balance is fragile, and we all have a stake in what tips the scale.